All right, I will get started. Let me begin with a word of prayer. So, dear Father, we thank you again for this day, for this class. Just pray you be with us, help us to glorify what we do and to understand what we need to about homotopy today, Lord. In your name I pray, Lord Jesus. Amen. Make sure I turn the mic on. It's always a bad day when the audio is not actually working. Oh, it's working. Woohoo! All right, so we have been talking about homotopy, and hopefully I will finish that thought today. And ideally, we'll start the next thing as well. So we'll see how that goes. I know you doubt it. I can sense it in the cough. All right, so the proposition. And this is proposition 1.12 in Hatcher. And here's what it says. The fundamental group of the Cartesian product of x with y is isomorphic to the direct product of the fundamental groups of x and y respective. If x and y are path connected. All right. So so the proof I thought was fairly easy to follow, so let's try to look at it. So he starts out by pointing out that, so let's think about this just generically for a second. So the fundamental group of the Cartesian product of an x and y should be based on looking at equivalent classes up to homotopy of paths on the Cartesian the Cartesian product of x and y, right? So you're looking at f, a mapping from, I to x cross y, right? Something like that. But such a thing you can write as like f of t is equal to, say, g of t comma h of t, right? Where here g is a mapping from I to x, and h is a mapping from I to y, right? And furthermore, Hatcher points out that continuity of f, right, using the product topology on x, the Cartesian product of x and y, well, continuity of f implies continuity of g and h, and I think vice versa, right? So f is continuous on I if and only if its component functions, g and h, are continuous, respectively. So what that means is that, so he says a loop at x naught, y naught in x cross y corresponds to loop at x naught and y naught, right? So you have, so you get a pair of loops for each loop in the Cartesian product. And he says, similarly, a homotopy of a loop in x cross y is equivalent so homotopy of loops in, x cross y. Let me use his notation here. Goodness gracious, what's wrong with me? FT, homotopy. Right. So again, the homotopy is what? It's going from the Cartesian product of like, well, it depends on how you look at it, I suppose. But if we go back to, oh yowzers, I don't know. He keeps switching the meaning of S and T here and there, so it kind of, I guess I'm kind of being dumb on some sort of having some sort of like dogmatic meaning of S and T as if they're, have to have a certain meaning. Because they, you could just use S and T as parameters. They don't have to have a fixed meaning in these different maps, obviously. But anyway, so this F sub T would give you a pair, let's say, of G sub T and H sub T. The homotopies, respectively, they would give you, so that, implies you get like a G sub T and H sub T homotopies of loops in X and Y, based at X naught and Y naught respective, right? So, in short, you can define the isomorphism just to be this. You take F, right, the equivalence class, the homotopy equivalence class of the loop in the Cartesian product, and what are you going to map it to? Over in there. In my current notation, you just map it to the equivalent, right. That's right. He says, this is obviously a group homomorphism and hence an isomorphism. Oh, well, he says I missed a sentence, it's kind of important. Thus, he says, thus we obtain, I'm sorry here. So he says, similarly, a homotopy F sub T of a loop in X cross Y is equivalent to a pair of homotopies G sub T, H sub T, and of the corresponding loops in X and Y. Thus we obtain a bijection from the fundamental group based at X naught, Y naught in X cross Y with the fundamental group of X at X naught, direct product with the fundamental group of Y based at Y naught, given by the thing I wrote on the board. He said this is obviously a group homomorphism and hence an isomorphism because he's just mentioned that it's a bijection. Is it clear it's a bijection? I guess it's clear. Well, yeah, I mean, I guess it's fairly evident that it's onto, right? If you pick any, if you pick any loop here and any loop there, how do you get, how do you construct the loop back over here? Well, you just, this right here, right? So it's clear that it's onto. And I guess it's also fairly clear it's one-to-one. So it's a bijection. And the homomorphism property, that is just this, right? If we had like two loops, F1 and F2, and we were, joining them, right? So F1, F2 in the Cartesian product would be this, right? But then over here, if you have, say, G1, H1, and you multiply it by G2, H2, how's that go? Well, by definition of the direct product of two groups, we just, multiply element-wise, right? Which then, by the definition that we talked about last time, the group operation in the fundamental group is just the join, you do the equivalence class of the join of the two curves, two paths rather, G1, G2, right? But if you sort through what the definition should be of this, you would see that well, what I'm trying to say is if you were to look at F1 join F2 of t, right, you could prove that that actually would give you the pair G1 join G2 of t, right, and H1 join H2 of t, which would then give you that you have the homomorphism property. So anyway, so there it is. That's a super super nice result. And so the if we think about the torus, right? Remember the 2 torus is just S1 cross S1, right? So we see that the fundamental group of the 2 torus is the fundamental group of the circle, direct product with the fundamental group of the circle, which is Z cross Z, right? From last time, fundamental group of the circle. And likewise, if you looked at the N torus, right, which is, so you can inductively extend this, yeah? So the N torus can be defined by just the Cartesian product of the circle, n-fold times circle. And so we get Z cross Z. Try not to put you to sleep here. There you go. He mentions that these sorts of things have been known in terms of knots on torus, or so-called torus knots. How do you understand these kinds of inequivalent loops on a torus? How the loops like wind around the torus in different ways and so forth. There's a somewhat ancient literature studying knots on tori, I think. Yeah, knot theory. Knot theory is, I don't know. I don't know much about knot theory, honestly. I know enough not to get into it, but sorry, it's
I know enough not to get
horrible.
Enough not to get tied up in it.
Not to get tied up in it. Yeah, it's just pretty good too. I see what you did there. It's not bad. But joking mostly aside, there was a time when Sir Lord Kelvin, I think it was Kelvin.
You look at a smoke ring.
He thought that there was like everything in physics, like physics could be fundamentally described in terms of knots. Like if you look far enough down, everything's just knots, you know? And so classifying different kinds of possible knots had physical significance. And so there's a whole bunch of people who tried really, really hard to understand all the possible knots in like the mid-19th century. And then at some point it fell out of disfavor, so people stopped working on knots.
Not so.
It was not, not so. Oh, I started this, didn't I? All right, so so the next thing I should mention a little bit about is if we have a mapping phi that goes from, say, a topological space X to a topological space Y, and say, suppose like phi of X naught is equal to Y naught, all right? Then, you know, you can kind of picture this. And if you have such a map, you can imagine, you know, transporting equivalence classes of loops over here, right, to like corresponding equivalence classes of loops over there. And I mean, he says it's called phi star. Phi star is the induced mapping. So this phi star here would go from the fundamental group of X, and I think we use this based at X naught notation. All right, and I skipped that. I mean, so usually the fundamental group is the same at different points, so we just drop the point. There's a whole bunch of technical development on that point in Hatcher, which I'm kind of skipping over here because I'm lazy, or out of time, or maybe both. But so that is the so-called induced homomorphism. The phi induces this homomorphism, phi star. And the definition is just this. So you do phi star of an equivalent, a loop here, all right? So like what is a loop? I mean, a loop is a path, right? It's a path. And so if I can fit it in here, so you got this unit interval from 0 to 1, right? And so basically, if this is f, yeah? You're taking a point here, say t, and typical point on here would be f of t, right? And I'm trying to use this path to create a path over here. What do I do? How do I get from here over to there? What do I do? I mean, I want to just do this, right? So I can do what? I can just go like this, right? So this mapping would be, let's see, the first shall be last, the last shall be first, phi composed with f, right? Then that takes it goes up here to f of t, and then f of t maps over to here to like phi of f of t, right? So the induced homomorphism is simply defined to be the equivalence class of what? Phi composed with f, yeah? So that gives us a homomorphism from the fundamental group of x based at x naught to the fundamental group of y based at y naught. All right? And he says you can prove that phi star psi star is equal to the induced homomorphism. If we do phi composed with psi, the induced homomorphism of that, it's the induced homomorphisms composed in the same order, all right? So I guess I can put in the composition symbols if you guys like. I mean, I don't know. I'll do it. Although it's not typically done at this level of math. At some point, mathematicians stop writing the composed with thing, you know?
Because they start becoming algebraists.
Yes, they do become algebraists. That's one thing. And the other thing is that the identity map, all right, so like the identity map on the space, so the induced homomorphism of that, it's, I guess, going to be the identity map on the fundamental group of the space, yeah? If I understand things correctly here. But of course, I guess I should probably, for a given point or something, there's some kind of point dependence you got to talk about there. Well, he says at x naught. So I guess there has to be a point given to do this. Fine. But he mentions here that this goes to show that you've got something called a functor, right? A functor. And then he says he'll come back to that in section 2.3. So I guess that's another semester for you guys. Sorry about that. Okay, anyway, so just want to talk just a bit about the induced homomorphism. We'll come back to that later today, just not yet. So next up, we've got proposition. So, I mean, what is a functor? A functor is something that goes between one category and another, right? So you got like, your category has your sets, like your typical objects, your typical morphisms, and a functor shows you a way to go between objects and morphisms in one category and objects and morphisms in another category. So a functor transforms both. It's some sort of like correspondence both between the sets or whatever objects define the category and also the morphism. So it's a kind of complicated business, but it just formalizes analogies that we notice in math. Like you've already started to see this probably, like we have isomorphism theorem in what? In like group theory, right? There's an isomorphism theorem in linear algebra. There is like this first isomorphism theorem is also in Lie algebras if you study it. There's a first isomorphism theorem in Lie groups. There is there's certain theorems that if you look, you keep seeing these theorems reappear in different branches of mathematics. Have this strong sense of deja vu in some sense, and like category theory in part formalizes some of those coincidences, right? I'm not being careful here. Yeah, they're not really coincidences because these are just, some of these theorems are categorical, and so they just have different instantiations in different parts of mathematics. All right. So for example, my brother studied infinite dimensional Lie algebras, something called vertex operator algebras at NC State, and a lot of other people who studied algebras around the time that Bill did, in fact, there's like a whole series of theses that were more or less based on taking theorems which were known for Lie groups. All right, so things that were known from, a Lie group is a manifold with group structure. And so there's parts of Lie group theory that have been very well studied, and there's some really deep theorems. And so one of the things you can do is say, oh, okay, well, is there a corresponding theorem in the category of Lie algebras, right? So how do you go between a Lie algebra and a Lie group, Well, if you could find a correspondence between Lie algebras and Lie groups, that would be like an example of a functor. So the exponential plays a role in this. You can exponentiate a Lie algebra to get a Lie group, in some sense. But anyway, I shut up about that. So proposition 1.14, and I won't prove everything here, but there is part that I think we can understand. So what I'm trying to do, guys, is look through this, and I'm looking for like sort of low-hanging fruit, which I think we can understand. And I'm trying to not get bogged down in the part which, would take a significantly larger amount of time to understand carefully. All right, so this is equal to 0 if n is greater than or equal to 2. Now, in contrast, when we turn the page and do the next topic, I will hopefully be pretty methodical and complete in my analysis. So it's not going to, like the next thing I do, I will be much more careful. So here it is. The fundamental group of higher spheres is 0 for n. So we what's the deal? Last class, I gave you 70% of the, 50%, 40%, whatever percent you want of the proof of this, right? Up to homotopy, that's right. That's right, up to homotopy. So we saw the proof of that. To deform my mistakes to 0, that'll work. So we have that. And he says this basically rests, a lot of this rests on a lemma, which I'll write out here. So here's the lemma. Lemma 1.15. If space X is a union of path-connected open sets A sub alpha, each containing base point x naught in X. And if each intersection, A alpha intersect A beta, is path connected, then every loop in X naught is homotopic to a product of loops each of which is contained in a single A sub alpha. All right. So the proof of this thing looks like a bowl of spaghetti. See here, it's right here. So we're going to skip this proof, but.
What do you mean loop in X?
Product each loop in X at X naught. Sorry. Thank you.
Does that have to be, does every path connected open set have to be, or does every open set have to be path connected to every other open set?
Well, if each one of them contains the base point X naught.
Right, then just make that.
Let me try to think of that. You can get intersections which aren't. Let me show you the issue. All right. I don't know if I can do it. Okay, so yeah. So here's the X dot. Aw, man. Right? So if you got the purple, you got the black. X naughts contained in both. They're both path connected, but their intersection is not path connected. Because the intersection of these two curves, intersection of these two open sets is this, right? And that, which is not path connected. So this is what's being avoided in the lemma's conditions. I'm particularly sensitive to this issue because it has wreaked great havoc in the problem of finding an atlas on a particular example of a sub-supermanifold I was interested in. It's exactly this intersection property that messed everything up. This is the reason for the piecewise linearity of the Frieze atlas that I told you about. The intersections, they got like two pieces. Anyway, so we don't want that. All right. So, given this lemma, which we're going to assume, we can express Sn as the union of two open sets. So, let's start out with S1 because it's a special case which actually doesn't, this fails for S1. So S1 is this, right? And if we were to take S1 and we could divide it up like this, you see you could say, well, you got this piece, right? And you got this piece. Right? So think about this as like A2 and the other one A1. What's the intersection? Maybe we can make 1 the base point, you know? Yeah, so like A1 intersect A2 in this case is, yeah, it's that, which does not meet the conditions of the lemma, right? However, if we think about like the 2-sphere, right, and think about, you know, on the one hand, like this, so like, you know, S2 minus the North Pole, and then you make, you know, I'm not going to try to do the same picture. You do S2 minus the South Pole, you know. Then when we intersect those two, we get everything, like you said, except for the North and South Poles. But now, good news. It's path connected. Now he says at this point, he says we can express Sn as the union of 2 open sets A1 and A2. Write this down here. So we've got Sn is equal to A1 union to A2, and I'm supposing that A1 is let's say without the North Pole, and A2, and if we can do it for 2, we can do it for n, yeah. N greater than or equal to 2, because as we've seen, n equals to 1 has a problem, right? Which is good. We also know that this is not true for n equals to 1, so that's to be expected, yeah. So we can express n as the union of these 2 open sets A1 and A2. He says each of which is homomorphic to Rn. He says A1 and A2 homeomorphic to Rn. Now you might wonder, what is this homeomorphism he speaks of? It's the stereographic projection. That's what we're talking about. So it's most familiar in the case of the 2-sphere. You think about the complex plane, and you connect the point on the 2-sphere to the point on the plane which is given by the chord which intersects the 2-sphere with the plane, starting at the North Pole, you know. There's a couple different ways to set up the stereographic projections. Let me not say more because like I don't want to get into those details. The point is that there does exist a one-to-one correspondence between and it's not, is it N? Is it Rn though?
Yeah, because it's Sn.
Oh, that's right, because Sn is fitting in Rn plus 1, right? So those are both homeomorphic to Rn. How about the intersection though? Can you guys see this? He says that the intersection is homeomorphic to what? Hmm. Hmm. So he says it's homeomorphic to, the intersection is homeomorphic to Sn minus 1 Cartesian product with the reals.
Actually, actually it makes sense.
Mm-hmm.
If you think about the middle, what do you call it? The equator
Mm-hmm.
as S1 in our picture up there.
Mm-hmm.
And then positive reals is the top, negative reals is the bottom. You like do some kind of
Yeah, I think, I think I almost immediately see like a homeomorphism between A1 intersect A2, right? And like S1, well, for me this is S1, but I guess technically it's Sn minus, the equator is Sn minus 1, right? These pictures are, this is Sn minus the north and south poles, right? But in this picture, if you can imagine this equatorial quote-unquote circle is actually Sn minus 1 in the natural identification. You're just freezing out that last Cartesian coordinate, and it still leaves you a sum of the squares of the remaining coordinates equals to 1, which is the n minus 1 sphere. Because the n sphere is immersed in Rn plus 1, the equatorial sphere is immersed in Rn. So it's one less dimension, Rn minus 1. But yeah, like you said, I see exactly what you're talking about, like this with minus 1 to 1, right?
yeah.
And then the thing is, in topology, you learn that there's a homeomorphism between any open interval and the whole reals. You can just play a game with like inverse tangent or something, right?
But there's not a homeomorphism between Sn minus 1 and Rn minus 1. Or is there?
No, Sn minus 1 and Rn minus 1 are different, yeah.
That's good.
Yeah. Okay, so, all right, well, let's complete I don't know if we actually need all that for all this, but, all right, so, all right, let's put our thoughts together here. So we should think about a loop. Think about a loop in Sn, right? It can be done, so since Sn satisfies the lemma, if we think about a loop in Sn, based at, say, 1, then we're supposed to be able to, it should be homotopic to a product of loops, each of which is contained in a single A alpha, right? But our alphas are just A1 and A2, right? And what if you have a loop in A1? What is the, A1 and A2 are homeomorphic to Rn. Remember, homeomorphism preserves homotopy, right? So like the fundamental group of A1 is equal to the fundamental group of Rn. But the fundamental group of Rn is trivial because Rn is convex, right? Any 2 points are connected by a line segment. So all paths in Rn are homotopic to the constant path. So this is just the, basically the set. It's the trivial group.
Greater than 2, right? Which is what you assume.
Well, the fundamental group of Rn is that's actually always true.
Really?
Yes.
You mean R2?
Yeah, the fundamental group of R2 is,
Oh, sorry, I was thinking about
it's all of R2,
punctured.
not the punctured.
I was thinking about the punctured.
Yeah. Right. So since that's trivial, and the same for 2 is trivial, you have a product of trivial, you have a product of, identity. The product of identity loops is again the identity loop. Consequently, phi1 of Sn is equal to 0. Again, we have to assume n is greater than or equal to 2 because the lemma doesn't apply and n equals 2 because of this. I thought this, I could understand this argument. I think it's pretty good. I mean, of course, I'm glossing over the technical lemma, but, you'll forgive me. So this implies that the fundamental group of Sn is equal to, or well, I guess we say 0. Let me stick with his is notation 0. All right. Moving on here. Corollary. R2 is not homeomorphic to Rn. Corollary. R2 is not So he's using a result here that he's studying, he takes a point away from the space and makes arguments with it. Do you guys remember that from topology? Like if you take a point away from the space and you take a point away from the other space and you can show that those are not homeomorphic, then the original spaces are not homeomorphic as well? I mean, okay. Well, I think that's going to be used here. So here's the proof. Suppose you have F going from R2 to Rn, a homeomorphism, right? A continuous map with continuous inverse. He says n equals 1 is easily disposed of since, so for n equals 1, we have if we take away a point from R2, right, is path connected, right? But R1 without 0, right, is, and this is not path connected, right? So he's using this, right? He's saying if you know, supposing that you have a homeomorphism, if that were the case, then it should still be the case that path connectedness. Okay, so I guess let's just think through it. Path connectedness is a property which is preserved by a homeomorphism, I think is what's going on here, right? So if I remove a point from R2 and then I look at the image of that under a homeomorphism, then I'm definitely missing a point in R1. But if you remove a point from R1, it's not path connected. But one of the properties of homeomorphism is that it preserves path connectedness. Right? Path connectedness is a topological property. Homeomorphisms they preserve all topological properties. Right? Path connectedness being one of them. I mean, that's the whole point of the fundamental group in part, is like it is a piece of topological data. It's something that has to be preserved by a homeomorphism, you know. Something else I wanted to say here. Rats, I can't remember. Okay, so that's the n equals 1 case. n equals 2, we're not, n equals 2, it is homeomorphic. It's the same stupid set, right? Any set is homeomorphic to itself. Duh. But if n is greater than 2, he says we cannot distinguish R2 with 0 removed and Rn with f of 0 removed by the number of path components. Oh, good, it is what I was thinking about. So if n is greater than 0, then, you know, R2 minus 0 and Rn with f of 0 removed cannot be distinguished the number of path components. Why? What is the number of path components of Rn with the punctured plane, right? It's path connected. It's got one path component. It's right? And likewise, if you take Rn and you remove 1 point from it for n greater than or equal to 2, it's path connected, right? So there's one path component. You can't tell the difference in terms of number of path components between these. All right? That's not making any progress towards the proof. It's just explaining why the first method of proof doesn't extend past n equals to 1. All right? All right. But he says, but we can distinguish them by their fundamental groups. He says, for a point x in Rn, the complement of Rn minus x, and this vexed me for a minute. See if you guys can understand it. Rn, remove a point, right? He says that this is homeomorphic to Sn minus 1 Cartesian product with the reals. So we'll stop here for a second before I get to the conclusion of the proof. Can you guys tell me why that's true? Let's do it for R3. Why is R3 with, let's say, a point removed? Let's make the point the origin just for the sake of specificity. You know, why is this homeomorphic to the two-sphere what's the homomorphism? How about this? It's the direction magnitude homeomorphism. See, the direction of a vector in Rn is on the n minus 1 sphere. It's a unit vector that points in the direction of the vector, right? And then its magnitude is a real. And then we use the the usual homeomorphism. 0 to infinity is homeomorphic to all of R, right? And so that's this. That's what that is. So it's polar coordinates, I guess, in 2 dimensions. It's spherical coordinates, and I mean, whatever you want to. This is the map. Almost. I mean, of course, this only gets us to what? Technically, this just gets us to. And then you need some other thing that you should have learned in topology that gives you that this is right. you can find a one-to-one bijection with continuous inverse that maps from the positive reals to the whole reals. What is that, by the way? What is the homeomorphism here? Can you guys tell me that one? I want G that goes from 0 to infinity to the whole reals. What should I use? How about G of t equals to natural log t? Then G inverse of y, let's say, would be equal to e to the y. Continuous, continuous inverse. That's the homeomorphism. I should have taught you guys that part of topology. It's easier. Well, it's easier right up until you ask the wrong question, you know? Anyway, where was I? Okay, so this is homeomorphic to that. Great. And then what? So this means that the fundamental group of Rn with a point removed, right? Because it's clear that we can, if we can do it at 0, we can just as well base our vector at x and, you know, do displacement vectors based at x, magnitude direction, you know. There's an obvious modification of that map to an arbitrary point. Anyway, where was I? So the fundamental group of Rn with a point removed is equal to the fundamental group of Sn minus 1 Cartesian product with the fundamental group of R, right? But what is that? So if n is greater than wait a minute. Oh man. Is n greater than 2 or is n is greater than 2 here, right? We're currently in the that was right here. I mean, I said it. I don't think I wrote it down though. But at this point, like right here, past this point, we're assuming n is greater than 2, right? N equals to 2 is not interesting. N greater than 2. So if n is greater than 2, what's this?
Greater than.
I have trouble with this today. I need to write greater than or equal to 3. I just feel better about it. I don't know what's wrong with me. But then I can see clearly that this is 2 at most, right? I mean, at small, at least 2. Thank you. Oh. So this is 0, and that's, of course, 0. And as such, this is 0. But on the other hand, I guess see, now I've muddied things up. But anyway, but by the same argument I just went through, if we put R2 minus, you know, a point, we do get pi 1 of S1 pi 1 of R, which is Z, which of course is not equal to 0. So since the fundamental group of R2, see, if the fundamental group, if in fact R2 and Rn were homeomorphic, then the homeomorphism would transport the fundamental group of R2 with a point removed to the fundamental group of Rn with a point removed. But we just saw that they're not equal. Consequently, it's impossible for R2 to be homeomorphic to Rn for n not equal to 2. Because we dealt with the n equals 1 case earlier. Does that make sense? I think it makes sense. You can disagree if you want. All right, so I think that's kind of all I want to say from from Hatcher. At this point, let's look at the handout by Zhao. I'm probably mispronouncing that, but skip to page 18, if you will. So this is like a pretty nice, crisp review of, let me just say what I'm looking at. This is, what's the title of this thing? These are freely available as a PDF online. It's roughly speaking notes kind of sort of based on Nakahara's Geometry, Topology, and Physics, which is a formidable book. I need to read again, actually. I think I've read the first edition. I don't think I ever actually got a chance to read the second edition of Nakahara. And I really should. It has some supersymmetric field theoretic proofs in it somewhere or another, I guess. But yeah, this is Lecture Notes on Geometry and Topology by Kevin Zhao. So I'm sure that was fuzzy. But, well, anyway, so page 18, he starts talking about homotopy groups, right? And so we did most of this already. I think you'll find this a useful, very quick review of some of those things. There's something else he had here, which was just, it was nice and crisp and clear. So I wanted to define that for you guys. On page 19, he has a proposition. He says, if x and y are homotopic with homotopy equivalence f, then the fundamental group of x at y naught is isomorphic to the fundamental group of y at f of x y naught. So the fundamental group is a homotopy invariant, right? And the proof is right there. So that's nice. And then this definition is also important. X, because I use this word, but I haven't really carefully defined it, so I wanted to. X and y be topological spaces with y being a subset of x, okay? A deformation retraction. Deformation retraction is a continuous map f from x, Cartesian product with the unit interval, back into x again, such that you have f of x comma 0 is equal to x, and you have f of x comma 1 is an element of y, and also you have f of y comma t is equal to y. Now he doesn't say, but this is for all x and x, I believe, and this is for all x and x, I'm pretty sure that's true. And this is for all y and y. I think that's what's meant there. He says this means that f shrinks the space x down to y. We say y is a deformation retract of x. So the picture is something like, this is x. Here's y, right? And so well, it's hard to picture f directly, but I sort of think of f as like shrinking x down to y. Yeah. But this is a deformation retract. And so here's the proposition.